Okay, let's settle down. We'll get started. Let me give you like 30 more seconds to settle down and. Okay, we're all good. Okay, welcome to University of Tennessee, Knoxville. My name is Ahmed Aziz. I'm an assistant professor of electrical engineering and computer science. I've been here since 2019, so more than 5 years now. It's a pleasure to see all of you on campus, and I'm going to talk about something which is of interest to the whole nation right now. How many of you have heard about computer chips, semiconductors? Many of you, if not all of you, at least many of you. Okay, so I'll talk about that chip design technology today, and I'll hopefully try to motivate you about the criticality of this technology, why it is necessary to care about chip design, and what can you do, how can you get involved, and what's the future. All right. Engineering is huge. There's mechanical engineering, civil engineering, material science and engineering, electrical engineering, as you can see, computer engineering, and aerospace. I mean, there's a whole host of engineering available over there, right? When you get to that level that you want to choose your college direction, you get the opportunity to pick and choose, hopefully. My intention is to at least give you one direction that you could potentially consider for your future. So without further ado, let's get started. As you see, my presentation title is Emerging Nanoelectronics, its Challenges and Opportunities. Obviously, I'll talk about some challenges that we're facing in our community with chip design, and I'll also show you some opportunities along the way. So, this is me. I just introduced myself already, so no need to go over it again. Let's start with some background and motivation, right? Shall we? So I decided to get and collect a lot of newspaper articles from all over the world about chip shortage. Have any of you seen any news about chip shortage over the last few years? I see, some people nodding, some hands raised, which is good. But if you haven't, these slides are for you. Not too long ago, like a couple of years ago, around the time 2021, 2022, there was a huge problem with chip shortage in the United States and in fact around the world as well. Car makers like Jaguar, Toyota, Audi, they were all cutting their supplies. Obviously, iPhones, game console makers, all sorts of companies, they started cutting down their supplies. Why? Turns out, chip shortage was the common culprit behind all of those supply shortages. And you might be wondering, how is computer chip related to car makers? I understand if Intel does it, I understand if Apple does it with their iPhones, but how is General Motors and Ford affected by computer chip shortage? I'll show you gradually, right? So apparently there is a link with what happens to the economy and how many chips you can produce in the United States. So you see so many major news articles about chip shortage. And let's move to the next one. Apple had to cut iPhone production due to this chip crunch, and when you cut production of a certain product, that means your bottom line, like the total profit that you get out of selling those stuff, will also reduce, right? Global chip shortage led to problems with PS5 selling. I felt that might be of interest to you. Microsoft, all those big companies, no matter how big or small you are, you feel the heat with chip shortage, right? Now, this article was really interesting from BBC. Why is there a chip shortage? You can Google it, you can read the article later on. It's necessary for you to educate yourself about the current affairs and what's going on in the world. Because soon, you'll be at the center of it. You'll have to make decisions, you'll have to solve problems, right, by yourself. Obviously, I'm not going to go through the entire thing. There's a small snippet that I took the screenshot of because I liked it. So apparently, it's not just like big companies, car makers and phone makers that suffered. Even smaller startups like a US farm that makes dog grooming kits, that was also struggling with chip shortage. Yeah, it's there, right there. If you read the article, it's difficult to point to, but you can Google it and you can find it. Why would a dog grooming machine maker suffer from chip shortage? Because that tells you computer chips are everywhere. They are there in space probes. They are there in F-16 fighter jets. They are there in your computers. They are also there in your toaster ovens, maybe in dog grooming machines as well. So chips are everywhere right now, even in the children's toys to some degree. All right, so now what should we do about it? Now that the United States suffered through chip shortage and we are still struggling to some degree, people decided to not do the same mistake again, right? So there has been a surge in investment, and we see the numbers, not only from the government but also from several companies. Apple committed to $430 billion investment. You know, that's a huge amount of money, by the way, right? If you think about it. Move forward. TSMC, $100 billion. Micron, $100 billion. How big is $1 billion, right? With $100 billion, you could have solved a lot of other problems, by the way. So you see, it is so important that companies are pouring in money, and these are always in tens of billions of dollars to hundreds of billions of dollars. So huge investment. I'm not going to go through the entire list. Intel, $20 billion chip in Ohio. Similarly, GlobalFoundries, $6 billion. All of those big investments are pouring in, which shows that in the future, you definitely have to take chip design very seriously. Where will all those investments go? They will create jobs, they will create opportunities, they will create new factories, obviously. And who will work on these factories? Who will work as engineers in those factories? This is probably going to be your generation, right? And the next generation and the next. Simply because you make $100 billion investment today doesn't mean that you're going to reap the benefit the next year. You're looking at the future, next several decades, right? All right. Having said that, the chip design industry is not a small targeted sector. There is a huge spectrum associated with it. This slide will tell you about it. This is known as the level of abstraction. So there are different levels of the chip design process, starting from materials all the way to systems. So in the material, how many of you have heard about silicon? Silicon Valley? Anyone? Why is it called Silicon Valley? Because a lot that happens there, chip design, that deals with silicon. Silicon is known as a magic material, for example. For the longest time, like for last several decades, we have used silicon to make computer chips. And we have done really well. But we are at a stage where silicon is struggling to keep up with our demands. So we are looking for new materials, right? And when I say new, it could be all over the place, from 2D materials to superconductors to phase transition to ferroelectrics. There's a huge spectrum of materials available for our next generation chip design. So as engineers, we have to deal with this intelligent, exciting material platforms and try to use them to design the next generation devices. And that's where you go to the next level of abstraction, to devices. We use materials to make interesting electronic devices that could do stuff, that could help you compute, that could help you store information, that could help you sense information, and stuff like that. Once you make devices, you connect multiple devices, and that multiple could be from 10 to 10 billion, even trillion, by the way, depending on how complex the chip is. Okay, you connect multiple devices to make circuits, and you use humongous amount of circuit assembly to make systems like, say, supercomputer or your Core i7 processor or other things. Okay, so let's move to the next one. In digital electronics, you could treat any system to be of different kinds. But I felt like these are the major ones. Some systems do computing. So you compute something, you add something, subtract something. It may not sound very fascinating to you. It's more like we are making calculators. But if I told you, how many of you heard about the term AI, artificial intelligence? Right? ChatGPT? I guess everybody have heard about it. So ChatGPT is an AI system, right? What if I told you most of the computation that occurs behind the decision-making process of ChatGPT and other AI systems is basically addition and multiplication? Wouldn't that be surprising? But at a huge scale. Trillions of addition, trillions of multiplication will basically lead to ChatGPT systems. So now hopefully you pay attention. It's not just calculators that you make out of adders and subtractors. So computing is at the core of everything. How do you simulate a new molecule to design the next generation vaccine, for example, right? When you simulate, you compute, you solve equations. And for computing, you use supercomputers. So there you go. You need a lot of computing power. When you send a rocket or space probe to a certain orbit, how do you calculate it to a so precise degree that you don't make any mistakes at all? You have to do perfect computing. So computing is a big aspect. Storage. You have to store information to even compute. right? You have to store information before and after you compute. So memory helps you store information. Okay. Next, sensor. You can always tell, like when you take a photo, you're using a sensor to convert something in front of you into some digital information, right? It is stored in your memory card as digital information. Okay. So sensors. This is just one example. There are temperature sensor, magnetic field sensor, all sorts of sensors out there that convert physical information into digital information. And very recently, this is a recent trend, people have started merging these avenues together. Can we bring compute and memory together to make compute in memory? Can we make sensors smart by doing computing in sensors? These are more advanced directions. But at the very least, compute, memory, and sensor are different kinds. Okay, now I want to use this example to show you how critical it is and how difficult it is to, do stuff in digital electronics. On your left, I mean wherever you are looking at, on your left there is a flowchart kind of thing which shows the core of any computing platform that we use in modern times. It's behind your iPhones, it's behind your like laptops, iPad, any other computing device you might be using. There is a memory block in it. There is a computing processor in it. For example, if you talk about iPhones, there are memories, flash memories. There are processors, like very advanced Apple processors, and they are separate. They could be separate. And we use some sort of communication between them. We fetch information from the memory to the processor. We do some computation, and we store it back to the memory again. So there is a lot of computation operations between the memory and processor. This is how we work. But just imagine how critical it is to maintain each and every bit in a precise way, so that we don't make even a single mistake. And this example will tell you what. So we know in English alphabet we have letters A, B, C, and so on. Engineers decided to represent every bit of letter as a stream of binary bit. Okay, this is known as ASCII code. So when you put a keyboard stroke, like you press A, the computer doesn't basically recognize A. It recognizes a bit of binary. What do I mean by binary? 1 and 0. Have you heard about binary number systems?
Yes.
Ones and zeros, right? Nothing else. May I ask, why is binary interesting, not decimal? Why don't we talk about decimal so often in digital electronics, just binary? Can anybody tell me? What's so special about binary number systems? What do you think? You can be wrong. It's okay, you can be wrong. Yes, go ahead. Anyone? Alright, since there are many of you, I can answer for you by the way. 1 and 0 sounds like on and off. Don't you think?
Yeah.
So basically, if you are just dealing with two digits, 1 and 0, you could represent those two digits with a switch that could be either on or off. So that's what we do in digital electronics. We create switches. We create a lot of switches to represent 1 and 0. Whenever you need to store 1, you'll keep the switch on. And if you need to store 0, you'll keep the switch off. So switches can be either on or off. That's why it's easy for us to deal with. Yeah, sure. It's easy for us to deal with binary, right? If you are dealing with decimal, for example, you have to store 10 different states of the switch, which is physically very difficult. All right? Does that make sense? That was a tangent, by the way. So let's get back to this. So every letter has an ASCII code. So there in the slide you see the ASCII code for C, the letter C, and the ASCII code for the letter B. Okay. So between the words cat and bat, there is just one letter difference, A and C. And within those letters, there is a binary stream that represents that letter. So C is represented by those 8 digits. It is agreed upon internationally. A or B or any other letter would be represented by a stream of binary. Do you notice that there is just one digit difference between C and B? Right? C has 8 digits, and within that there is one digit that is different from B. What if the switch that is representing that digit for some reason is not working well? Malfunction. Instead of staying on, it stayed off, or vice versa. Then you could convert a 0 to 1 or 1 to 0. So you could just convert your Batman to Catman, right? So very simple example, very benign one. But imagine that happening to your bank account, right? You had $1 million, all of a sudden one digit flipped from 1 to 0. It could be a disaster. So similar situations could occur if you are not careful, if you are not maintaining utmost precision in your design, verification, and usage. That's how critical digital information is. Even a single digit mismatch could lead to disaster. Okay. All right. So some interesting history. I hope this will be of interest to you because it will show how the field progressed. This is where we started back in 1958. This was the very first chip or integrated circuit that was designed by Texas Instruments, right? And around the same time frame, another company called Fairchild Semiconductor, they also designed a chip which is like 3 years apart. So they basically deserve credit for co-inventing integrated circuits or chips. Okay, and I guess you guys all know about resistors, capacitors, inductors, right? If you deal with resistors, capacitors, inductors separately, that's not an integrated circuit, that's discrete circuit. But in an integrated circuit, we bring different components together, we merge them in a way so that they have one coherent purpose. And then, if one of them is, for some reason doesn't work well, the entire thing is useless. Okay? So there is a risk. The good thing is they will be super efficient. The bad thing is there will be huge risk. If one of them malfunctions, it's gone. Entire thing is gone, right? So the more component you bring in, the more risky it gets, as you can tell. The first IC had one transistor. You may or may not know what a transistor is, but I'm going to tell you. Remember, I just told you about a switch that we use to represent 1 and 0. Transistor is that switch. If the transistor is on, it represents 1. If it is off, it represents 0. Okay, so just keep that in mind. Okay, so you had one transistor, 3 resistor, and 1 capacitor in a chip. Now, tell me something. One transistor is a switch that could represent 1 digit. Remember, 1 digit, right? That chip had just one transistor which could represent 1 binary bit. It couldn't even represent A, B, or C, not even a single letter. You see that? Our modern day computers can deal with video, audio, letter, whatever, you name it, right? Right? Typing letters is not even a challenging task anymore. But this chip wasn't even able to handle a single letter. Can you imagine that? Because it had one transistor. You need 8 transistors at least to represent just 1 digit or 1 letter. Am I making sense? Folks? Okay. But that's where we started, by the way. Yeah, sure, may not be that much of use, but at least that's where we started. Fast forward a few years, 1970s. This is the first ever microprocessor that Intel produced, Intel 4004 processor. It looks, zigzag because at the time people used to make things, draw things using pen and pencil, and there was a lot of manual intervention involved. Fast forward even further, this is one of the more advanced chips from Intel. It's so complicated and there are so many components, you can even count. See the numbers. Billions of transistors. You see that somewhere written there? Billions of transistors. That shows this chip can deal with how many digits at a time? Billions. Are you guys still with me? Yeah. Instead of just dealing with 1 digit, now we can deal with billions of digits. This is from AMD, another processor, still in billions, by the way. We don't talk in terms of millions or thousands anymore. We talk in terms of billions and trillions now. Okay? We started from 1, and we came a long way. Just call it a tremendous progress. Okay, I want to do a one-on-one comparison now. Take a very close look at this guy, because this is a celebrity in engineering community. This is the first ever processor, world's first processor that Intel produced. Okay, isn't that special? In 1971, Intel 4004 processor. This guy had over 2,000 transistors in it, so it was a celebrity of its time. See, 2,000 bits at a time. So what? Same company. Fast forward to 2021. Not even the most advanced one, right? 2021. Core i9 processor has more than 10 billion transistors. So it's not just you have more transistors. Each and every of these transistors is 7,000 times faster than the ones that we had in 1971. So we are getting more transistors and faster transistors. That's why we could do a lot more with our modern day chips than we could do in the past. Are you still with me?
Yes.
Alright. By the way, please feel free to stop me at any point and ask me questions. Okay? I'm not trying to go to any degree of technicality here, right? It's all higher level. a little bit superficial to give you the big picture. But if you feel lost at any point, please stop me and ask me questions. I think that's how we could best use our time. Alright, let's move to the next one. Even that 10 billion transistor is not the celebrity of all time. This is world's first trillion transistor chip. So there is a race going on among different companies to make the processor with the most transistors. Okay? Can anybody tell me what is the benefit of having many transistors in a chip? Can anybody tell me? Yes. Thank you. Perfect. More computation. So if I told you that I'm playing a game with like really high definition graphics, don't you think you need a lot of computation power to handle that game? Do you think that? Yeah. Okay. How about you're running a fighter jet which is running so fast and it has to predict a lot of things? Do you control that manually? No, you need a lot of support from instruments. And those instruments tell you, oftentimes it's in autopilot, for example. So it basically drives itself. Think about a Tesla or other electronic vehicle, EVs that drive themselves. So they have to analyze a lot of things simultaneously and make a decision. So a lot of computation. Okay? So if you don't have many transistors, you will not be able to deal with many binary bits at a time. So you'll be slow. If you have 100 transistors, you can only deal with 100 bits at a time. With 100 bits, you cannot even store a single text file. Okay? Forget about audio or video. Videos require billions of bits, basically. So if you have billions of transistors, you can use this to handle a high definition video, for example. Am I making sense? Yeah. Alright. So look at NVIDIA. NVIDIA has a chip with 54 billion transistors, for example. So many transistors. So there is a race going on to put in more and more transistors on chip. And the reason, I hope you now understand. Okay. I'm going to take another slide to explain what happens to the memory. Why memory again? Remember the slide before when I talked about 3 avenues that we care about: computing, storing information, memory, and also sensing, right? So it's not just going to suffice to have more computing power. We also have to store that information somewhere. If you don't have any ability to store the video or the game, how will you even run the game or compute anything, right? You have to store it somewhere. So we have to have matching storage. Use the same company as an example, Intel. US homegrown company, obviously. So what could be better than Intel as an example? So 1971, Intel had a memory chip with 1 kilobit storage. Folks, take a second to think about it. If you take a selfie, can anybody tell me an approximation? How much could be the size of that selfie? Would it be kilobit? No. Megabytes? You know the difference between kilo and mega, right? At least 1,000. You cannot even store a selfie with that thing, right? So just imagine how useless this would be in modern standards. Fast forward to 2021. This is a random access memory, RAM. When you buy computers, you probably see i7 processor, 32 gigabytes of RAM, right? So the more the better. I hope you know that, right? But I hope you now understand why more the better, because it could deal with a lot of binary information simultaneously. Okay, so 32 gigabytes. So let's compare between these two cases. That's a 32 million times enhancement. 32 million times enhancement in storage density within a period of 50 years. Can anybody give me an example from any other field? Anything that improved a million times within 50 years? What improved a million times? Can anybody give me another example? What improved 1,000 times? Communication? Yeah, sure. The reason why communication enhanced was actually also because of electronics, but that's a good try. It's a good thing, obviously. But million times? Forget about 32 million times, right? So this is insane, to say the least. Insane amount of progress that the engineers were able to make over such short time. Question: how did we make this happen? How did the engineers make it happen? Any idea? You guys are all using electronic devices, I'm sure. Smartwatches, smartphones, tab, laptop, television, whatever. I bet you have some of this, right? Could be multiple of this. But we don't even realize the marvelous engineering that is going on behind realizing those stuff. One of the reasons, actually the main driver for such a dramatic improvement is known as Moore's law. Intel co-founder Gordon Moore declared in one of the meetings, actually a conference, that every 2 years we'll be able to double the number of transistors on chip. Why is that important? When you double the number of transistors, you can deal with double the number of bits. So you have more computing power. So his engineers at Intel, they took it, our boss said so, we'll make it happen. So they are so good. It's not even a law, but they took it upon them as a law, and they start calling it Moore's law. Okay? So, and just look at the line. You don't even have to look at the numbers. It's a really nice trend line which showed you're able to follow along that line. Okay? In doing so, they started putting in more and more transistors on chip and making it more computationally powerful. Now, one quick question. Do you think from 1971 to today, our computers got bigger and bigger and bigger? What happened? Smaller and smaller and smaller. But we are having more transistors. How is that possible? More transistors, smaller processors. That means all those transistors must be really, yes, small, microscopic, right? As you can tell. So we are making those transistors smaller and smaller and smaller. That's what this slide shows you. With every generation, we are making transistors. They are not drawn to scale, by the way. We are making transistors smaller and smaller and smaller. Okay? And in doing so, we managed to put in more and more transistors. Now, take a very close look at these slides. These are taken, I took these photographs myself, by the way, from Intel Museum in California, Santa Clara, Intel headquarters. If you ever visit, you can go and see it for yourself. So this shows you the real image of an actual processor, using obviously microscope. If you see the leftmost image, the size of the image is the same as the tip of a pencil eraser. Okay, just for scale. Can you tell me how many resistors, transistors are there? Can you see the components? It's all zigzag, don't you think? Okay, zoom in further. Let's skip a few things. Get to the third one. Grain of sand. So the size of any side of the square would be the same size of the grain of sand. Can you see anything there? No, still zigzag. Zoom in further. Now you are looking at the diameter of a human hair. It's so small. You see some patterns, but you have no idea what these patterns are. Okay? I'm just going to tell you, this is nothing. You don't see anything yet. Zoom in even further. The leftmost figure. Now you are looking at the size of a bacteria. You see some pattern here? Look closely. Some horizontal lines, some vertical lines. They are not even the transistors that we are going after, by the way. They are the metal lines that we use to connect those transistors with each other. Okay? If you have billions of transistors, will you just sprinkle them around, or will you have to connect them with each other? What do you think? You have to connect them in an intelligent way. How do you connect them? You use metals to connect transistors. Okay? These are just connections. These are not even transistors. Zooming even further and further and further, thousands of times further, and at the very last image on your right, you see the transistors. They are so tiny. They are smaller than virus and bacteria. And there are billions of them. Now, let's pause for a second. Hear me out again. We are dealing with components that are smaller, many times smaller than bacteria and virus. There are billions of them, even trillions of them. We have to connect each and every one of them in a perfect way with each other. And we have to make sure everyone works. Not even a single failure can be tolerated. How is that for an engineering challenge? What do you think? Is that a small bit? Like if we decide to do, let's do chip design tomorrow. Let's make our chip design infrastructure better. Can we do it next day, next week, next month? It's gonna take a lot of effort for us to even get there. Okay, that's why $100 billion, $10 billion investment pouring in, because they are looking at the future. It's super complicated, very difficult to understand and work on. But I take that back. I'm not gonna, put it in a way that you cannot do it. Anyone can do it if they want to, but you just have to have the will. If you see the wonderful engineering that went behind over the last 50 years to realize this, and if you want to be part of the next 50 years, do consider this. And it's definitely doable. Anybody could get in and educate themselves in chip design and do something meaningful. Towards the end of my lecture, my presentation, I'll show you some initiatives that we have taken at University of Tennessee to achieve so. Alright, so moving forward quickly. This is a very busy slide. This is taken from a research paper published in Nature Electronics, a very famous journal. I'm not going to go through this. I'm just going to show you and point to one thing. Can you see a really nice straight line going from left to right? A straight line? Can you guys all see that? And the dots on top of that line? That trend line is what Gordon Moore predicted. He's Intel's co-founder, by the way, right? He predicted this could be a possibility. And engineers tried to work hard and they made it happen. You see that? All those dots are falling exactly on the line. Can you see a problem? Anyone? On the x-axis, what do you see? These are years. Starting from 1997, say, for example. So almost every year we are able to meet our target, except for the recent years, right? We're in 2024 and we are deviating away from the trend. So it has become more challenging to meet that demand that we set for ourselves, right? It's very difficult to keep up right now. It's very challenging. There are many reasons. Can anybody guess the reason? Anyone? What happened to the transistors over all these years? They became bigger or smaller? Yeah, go ahead.
Well, with the massive amount of businesses that use a lot of technology, they need more resources. So with the low amount of resources that they need, everybody's trying to get the same resource.
Absolutely, you were right. You pointed out one very big issue behind it, but there are many other reasons, and I would point out one technical reason. Okay, the technical reason is when you make things smaller and smaller and smaller, you are basically approaching atomic dimension. Right now, we can count the number of atoms in a transistor between two, source and drain, between two terminals of transistor. Okay, it's so tiny, so small. You see, they are smaller than virus and bacteria. What can you expect, right? So when you make things smaller, you have to deal with quantum physics. Heard the term quantum mechanics, quantum physics? Have any of you watched the movie Oppenheimer? No? Okay. Sure? But anyways, you don't have to, but it's fine. But just keep in mind, when you deal with small things, you are dealing with quantum mechanics, which is challenging to deal with. Alright. Now, I'm going to show you a quick video, 1 minute video, just 1 minute. But I think you should definitely pay attention to it. It's going to show you what happened to the semiconductor or chip design industry over the last few decades. And there is a message for you over there. Okay? Are you guys ready? Okay. Let's get started. What's at the top? This is a number. This is a ranking of different companies. Top 15 actually. Who's at the top? You see the flag? It's Japan. Okay? Where is US? Where is Intel? Somewhere down there, right? There are companies like Motorola, TI, Texas Instruments, many other companies. There are many players in the market, by the way. From Europe, from Asia, from obviously US is there. At some point around 1990s, Intel took over as the #1 semiconductor company in the world. You see that? Okay, so they reigned supreme for a while, and they were doing really, really awesome. If you keep looking, it's gonna be over soon. And just maybe focus on one company and see what happens to that company. You don't necessarily need to focus on Intel, for example. You will see no company will survive forever, right? At some point you're #1. Sometimes you'll be completely out of top 50, right? So things are dynamic. If you're not innovating, if you're not making new stuff, you're not making progress, you're out of picture. See how much of a lead Intel had in 2001? No one else was even in the picture, by the way, right? If you compare them with Intel. Samsung became #2 player. They were not even in the picture when we started, by the way, right? 2004, Texas Instrument is still #3, around 2005. That's also a US company. There are many companies that you see here, say Freescale Semiconductor, they will be out of business, by the way. Anyways, it's going to be over soon, don't worry. it appears slower than I expected, but you see that there is a lot of competition from other countries as well, other companies, and new companies come up and they take over. They get to top 5 all the time. Like Qualcomm, you see, notice that company Qualcomm. It wasn't even in the picture, by the way. It was a startup, and all of a sudden it's going to number 3. So you can have a really nice idea, and you create a company, and you get to the top. All right. It's almost there. 2015. So there is a race going on between Samsung and Intel. Looks like. Uh-oh. You see that? You see what happened? Around 2017, Intel is no longer the top player. And by the way, this is not the end of the story. There are more bigger players now. I don't have the data for it. I don't have a nice video to show. But remember, there are bigger players. So US companies no longer has, an advantage in terms of technology leadership in chip design. So that's a really worrisome trend. Okay, and by the way, I wanted to show you another quick video, as to how one transistor can be made. So you start from sand, literal sand. You melt down the sand, you make a mold of silicon, you cut down them into smaller silicon wafer. You do chemical mechanical polishing like what you're looking at right now. I just want to show you how complicated it is. You use light. You use light to create this small pattern. How can you create this tiny pattern? So you use light. Okay? And then you use some chemical dopants to change the properties of those silicons, like this. And after you're done doping, I'm not even going to try to talk about the details of these processes. There's a lot of etching involved, a lot of chemical processes involved, a lot of patterning involved, and just look at the intricacy of this structure. And that's just one transistor. How many do you need? Billions, even trillions. Okay? Can you make them individually? No. You have to automate the process. So you have automated process and industry that makes them in bulk, in trillions. Yes?
How long does it usually take to make?
Great question. Like I said, we don't make just one. We make billions and trillions. We make them in batches. Typically, from start to end, it could take months. It could take 6 months for a wafer to go through the entire, depending on the complexity of the process. That's a great question. Right? So, you see, it's still going on. I kind of gave up explaining it because there are too many steps, right? After you make one, you just literally repeat the process, and then you have to connect them with metal. Those are metal ones, by the way. And basically, this is happening at the chip scale, billions and trillions, right? And in the end, you get silicon wafer. Every rectangle is a chip. You cut them like you cut pizza, for example. So you make multiple chips in one silicon wafer, and you package them. This is what packaging is, so that it's safe from external environmental anomalies, and then you sell them as a product. Obviously, before selling, you have to test and then you sell them. Okay? Alright, so that brings us towards the end of my presentation. Just want to show you how diverse this domain is. There are two major avenues. Low power electronics that targets the devices that you all interact with. Smartwatch, smartphone, laptops. Why are they low power? Because they have to be charged. You don't want to keep charging your devices, so you have to make sure they take lower energy to run. So there's a huge market opportunity there. Number two, high performance electronics that don't care about power, like military applications, supercomputers, automotive, right? Space electronics. You just need precision, accuracy, and most performance. You don't care about saving power there. Extreme electronics is getting a lot of attention. For example, we are sending a lot of stuff to space, and we plan to go to moon again. So obviously, space electronics is picking up. So is say hypersonic missiles. How many have heard about the term? If you haven't, basically this is dealing with extremely high speed missiles, right? And when something moves at really high speed, that heats up, the temperature goes beyond the capabilities of our regular electronics. So extreme electronics is getting into the picture. Just take a look at that image of a car, and all those other words that you see. These are electronics that go into a conventional car, not even a smart EV like Tesla, for example. A conventional car has a lot of electronic chips in it, starting from lane departure warning system to automatic braking to blind spot monitoring to your music there. There are so many electronic chips inside a conventional car, which is essentially known as a mechanical machine. Okay. Now, what's next? So I talked about this wonderful stuff with 10 billion transistors, 32 gigabytes of storage. Imagine what happens after a few decades, in 2050, for example. So things will be even more dramatic, right? So we have to make sure that we keep up with this trend of improvement, and we keep contributing to this field to keep it going. And that's what we are trying to do as well. That's what brings me to my research lab. My research lab here is called Nanoelectronic Devices and Integrated Circuits Lab, or in short, Nordic Lab. I have many graduate students. One of them is with us as well. Mazhar is with us. He's a PhD student. Thank you, Mazhar, for helping me with the presentation today. We still have a couple of days left. So the thing is, in our lab, we do a lot of chip design work, as you can imagine, right? That's why I'm here talking about chip design. We have to use a lot of equipment. So as you can imagine, to test these sophisticated devices and systems, you need sophisticated equipment, right? So there are 4 different avenues involved here. Simulation. You cannot just go and start making stuff and see whether they work, because these are expensive. They take a lot of money to make and test, okay? So you have to do a lot of simulation using sophisticated software. And these softwares could be extremely expensive. I'm not going to give you some numbers, but later on, maybe at some point you figure out. But we have access to those softwares, and we use the same softwares as Intel, NVIDIA, and all those big chip makers use. We use those softwares to test ideas, optimize our design, and then we can make them from commercial foundries, right? And then once we get those designs back, we have to test them. And we use this type of system called probe station, which could help you probe into those tiny little transistors, smaller than 5 FFT, as you can imagine, right? You can have probe tips connecting to those transistors, and you can test whether they work. Am I making sense? If you test one of them, you could rest assured that the others will also work. Okay? So this is like some images from our. That's a closer look as to how that works. You have a microscope that cylindrical thing that you see. You put your sample inside it. You have some probes that go inside and connect to different parts of the device that you developed and fabricated, and you test them. You test whether they work properly. Okay, in the lab. So I'm going to give you a very quick lab tour after this. Obviously, unfortunately, I cannot run the machines because it takes a long time to get started, and then to show you the process, because it's very precise. It takes a long time to get to the pad and connect that properly. So I'm going to show you the machine and talk about and maybe answer a few questions that you might have. I'm going to end with this slide actually. This is another initiative that we have taken in very recent times, actually this semester, funded by National Science Foundation, NSF. This is Advanced Semiconductor Design Program at University of Tennessee. Who is it for? This is for high school students and community college students. So we have several high schoolers and community college students who come every week, and we teach them chip design, basically. So ground up. We don't expect any parallels. We start from 0 to the end, so that they could actually end up with designing a chip and show it to NSF, for example, right? We started basically. This semester is our first batch. How much does it cost? It's free, basically, for everybody. So NSF is paying for it. National Science Foundation is paying for it. It's free for the students and everybody. As of now, we have 4 high schools from the Knoxville area. But keep it in mind for future opportunities. We hope that it will be a recurring opportunity for everybody else. And we have created a YouTube channel. This is a QR code if you're interested. We decided to upload all of those lectures for free for everybody to listen. So if you want to remotely go through this process, feel free. We are also uploading other lecture videos related to small concepts about chip design and others. Okay? And we are trying to do it in different languages. We are trying to do it in Spanish, English, French, and some other languages. Because I have students from different background in my lab, thankfully. So they are helping me create this content so that we have broader footprint in the world. So with that, Consider this, at some point in the future. I would like to end with this. The best way to predict the future is to invent it. Okay, so you are our future. Let's take part in reinventing or inventing our future together. All right. Thank you. I'll stop there. So if you are ready, we can start the lab.